Welcome to the next lecture on Synchronous Machines course. In the previous class, we completed our discussion regarding the construction part of a synchronous machine. We have seen what is meant by salient pole synchronous rotor and also what is meant by cylindrical rotor synchronous rotor and what are the measures we are taking in order to make flux more sinusoidal in nature. Okay. Now let us move to our next concept, that is about EMF equation of alternator. So before discussing about EMF equation, we need to learn certain mechanical terminology of armature winding. Okay. First of all, let us see how EMF will be induced in armature winding of a synchronous machine. Okay, see here. As I told you, in synchronous machine, armature winding will be available on stator part of the machine. Okay. Armature winding will be available on stator part of the machine, and in most of the synchronous machine, armature winding will be always three-phase star connected winding. Okay, so on the stator part we have a three-phase star connected armature winding. Okay, this is how A phase, B phase and C phase. And most importantly, armature winding in synchronous machine is a concentrated winding or distributed winding. Definitely it is a distributed winding. But what we can do here is that mathematically when we are developing EMF equation of alternator, first we will try to calculate induced EMF for a concentrated winding and then convert that concentrated winding EMF to distributed winding EMF. This is our goal. Okay, first thing is calculate induced EMF for a concentrated winding, just like a transformer, and then convert that induced EMF for a distributed winding, because calculating EMF for a distributed winding directly, that too mathematically, may not be possible. So we will calculate first for concentrated winding and then we will convert it to distributed winding voltage. Anyhow, this is armature winding of a given synchronous machine. Now the rotor part of synchronous machine consists of field winding. Okay, we know that. And important thing is the field winding of this rotor, or you can say alternator, is always excited using DC supply. Okay, this is the external DC supply. It may be a battery, it may be a DC generator, it may be a rectifier voltage, anything it may be. Using the help of slip rings, this DC supply will be connected to field winding of synchronous machine. This is called as field winding. And the current carried by this field winding, we will call it as field current. And whatever flux created by this field winding, we will call it as field flux. Now that field flux which is created by field winding of synchronous machine will cross air gap. Okay, will cross air gap and will link armature winding. Okay, so which flux is linking armature winding? The flux created by rotor winding, also called as field winding. As it is a field winding, the flux created by that winding is called as field flux. And this field flux will cross air gap and will link stator winding, also called as armature winding. Therefore, an EMF will be induced across this armature winding, and that EMF is called as field induced EMF, also called as generated induced EMF. In some of the literature, it is written as field induced EMF. In some of the textbooks, they use it to write it as generated induced EMF. Anything is correct. Why it is called as a field induced EMF? Because this is the EMF induced with the help of field flux. That's why it is called as a field induced EMF. And don't forget that induced EMF equation will always be developed per phase. Okay, number of turns per phase, flux per pole. Okay, like that we will get induced EMF per phase. When you know per phase induced EMF, and all the three-phase induced EMF will be displaced by 120 degrees, so that we can calculate line voltage also. Understand? So our target is develop a mathematical equation for induced EMF per phase in the stator part of the alternator, and the stator winding is also called as armature winding. As it is armature winding, in some of the textbooks, they also use it to write this EMF as EA, that is armature EMF, or generator EMF, or field EMF. Why it is written as field EMF means because it is produced by field flux. Okay, so the concept here is very simple. We will excite field winding with DC supply, so it will create a time invariant magnetic field. That time invariant magnetic field will cross air gap and will link stator conductors. The moment when you try to rotate that rotor, an alternating EMF will be induced across armature winding, that is called as field induced EMF. So we need to develop a mathematical equation for field induced EMF. So what we are going to do is that first we will assume armature winding is a concentrated winding and then convert that concentrated winding induced EMF to direct, or you can say distributed winding EMF. Okay, but to understand the difference between concentrated winding EMF to distributed winding EMF, first we need to learn what are the different terminologies that we will use for armature winding, then only EMF equation can be understood very clearly. Okay, alright, now the first important terminology word that we are going to study is pole pitch, also called as pole span. So we studied about pole pitch even in DC machines course also, and the same definition is valid for synchronous machine as well. So first of all, what is mean by pole pitch? See, there are two definitions. I wrote both of them. Read the first one. It is the electrical space angle between two adjacent north and south poles. Okay, most importantly, it is the electrical space angle between two adjacent north and south poles. And there is one more definition. It is the electrical space angle occupied by one complete pole or each pole. Okay, anything will give you same answer. So let us exactly understand what is this pole pitch or pole span. Okay, so see this picture, a simple picture I will draw to understand this pole span more clearly. Assume we have a 4-pole rotor or stator, you take anything. Let me consider a 4-pole rotor here. You can take a 2-pole machine or a 6-pole machine or 10-pole machine, any number of poles. I took a 4-pole machine to understand it easily. Okay, this is a 4-pole rotor. Assume here we have a north pole, south pole, north pole and south pole. Now tell me what is mean by pole pitch. It is the space angle between two adjacent north and south poles. See, we have a north pole here and we have a south pole here. Now, the angle between this north pole and south pole is what we will call it as pole pitch. This is nothing but pole pitch. But important thing is, directly if you look at this diagram, how much is this angle looks like between a north pole and a south pole? Exactly looking like 90 degrees. So whatever the exact angle by eye you are physically viewing here is nothing but a mechanical angle. Okay, so the mechanical angle is equal to 90 degrees in this diagram. But as I told you, mathematically we have to express everything in electrical degrees only. So that is why I wrote here, it is the electrical space angle between two adjacent north pole and south poles. So even though mechanical angle is equal to 90 degrees, what will be the electrical angle? Because I told you relation, electrical angle is always equal to P by 2 times of mechanical angle. It is a 4-pole diagram, 4 by 2 into what is the mechanical angle you are observing? 90 degrees. Therefore, electrical angle is equal to 180 degrees. Like that, you take any number of poles, the angle between two adjacent north and south poles is going to be 180 degrees only. Okay, the angle between two adjacent north and south poles is going to be 180 degrees electrical always. Mechanical it may be different. Suppose if I take a 6-pole machine, then the angle between a north pole and a south pole may not be 90, you will observe only 60 degrees. If I take a 12-pole machine, it will become only 30 degrees. But when you convert to electrical degrees, every time pole pitch is going to be electrically 180 degrees only. Why it is electrically 180 degrees only? The reason is very simple. You see, north pole, exactly this is a polar axis, right? The axis passing through the pole. North pole means positive maximum, south pole means negative maximum. So if you draw a waveform, mathematically when you try to express from a positive maximum value to negative maximum value, how much angle will be available sinusoidally? 180 degrees. This is electrical angle, right? Mathematically, whenever I am expressing, a flux wave or EMF wave or anything, I have to represent in electrical terms, and electrically from a positive maximum to negative maximum, there will be 180 degrees only. That's why pole pitch is always 180 degrees electrically. And there is one more definition available. What is mean by pole pitch? It is also the electrical space angle occupied by each pole. Occupied by each pole. Suppose if you take only this north pole, you see this is one interpolar axis, right? A Q axis. And this is going to be another interpolar axis. Now tell me, what is the space between this interpolar axis and this interpolar axis? Can I say this entire space is now the effect of this north pole? And this is also called as a pole pitch only. And if you physically see, what is this angle? Again 90 degrees. But when you convert to electrical, it will be equal to 180 degrees. Okay. So pole pitch can be defined in two ways. It is the angle between two adjacent north and south poles, or it is the angle occupied by one complete pole. From this interpolar axis to this interpolar axis, there will be exactly one pole effect, that is north pole effect, that is also called as pole pitch. So pole pitch is always 180 degrees electrical, 180 degrees electrical. Okay. Alright, now the second important term we need to learn is coil pitch, also called as coil span. Coil pitch or coil span. So let us exactly understand what is this coil pitch or coil span. First of all, what is mean by coil? I no need to explain much. In DC machines, I told you enough about what is mean by a coil side, okay, single layer winding, double layer winding. Okay, anyhow, let me introduce again. We know that a coil will have minimum one turn, maximum any number of turns. We can have a one turn coil, we can have a two turn coil, three turn coil, like that n number of turns may also exist in a coil. First you see, suppose if you consider a one turn coil, this is just a one turn coil. It has how many conductors? Two conductors. One conductor will be placed under north pole, the second conductor will be placed under south pole. Therefore, north pole, suppose if this is the voltage polarity, south pole side the voltage polarity will be exactly opposite. So, now the top one becomes cross, bottom one becomes draw. Now, when you connect this dot polarity to cross polarity, voltages will aid or subtract? Yes, aid with each other. Because when two opposite polarities are connected, voltages will always aid. Suppose if this voltage is E, this voltage is E, the resultant voltage is equal to 2E. This is a single turn coil. Like that, we can have a two turn coil also. You see, this is one turn. If I continue, this is going to be the second turn. Now you tell me how many conductors are there in this coil? There are 4 conductors in this coil. This is called as a two turn coil. Like that, we can have any number of turns also. Suppose if you wanted to draw a multi-turn coil, you see this is one turn. Next, this is going to be the second turn, third turn, fourth turn, fifth turn, sixth turn. Like that we can have any number of turns. But whatever may be the number of turns, how many terminals will be accessed outside finally? Only 2 terminals will be accessed. One will be positive, another one will be negative. So whether it is a one turn coil or two turn coil or multi-turn coil, the output terminals are only 2. One will be positive, another one will be negative. And in all these coils, okay, this end is always placed under north pole, the other end will be placed under south pole. And this end is called as one coil side and this end is called as another coil side. So a coil can have how many number of sides? Only 2 sides will be there. One side, the other side. How many number of turns may be there? Any number of turns. It may be a 1 turn or 2 turn or 3 turn or any number of turns may be there. You see, this is a 2 turn coil. Now these two conductors will form one coil side. These two conductors will form the second coil side. It is a one turn coil. This is one coil side and this is another coil side. So like that, a coil will have only two sides. One will be under north pole, the other one will be under south pole. But a coil can have any number of turns. One turn, two turn, like that many number of turns may also be there. Now, once you have idea about coil, let us understand what is meant by coil pitch or coil span. Okay. Now, let us see what is the definition for coil span or coil pitch. Read the definition. It is the electrical space angle from starting of a coil to ending of that coil. Very simple. I told you a coil will have two sides. This is one side of a coil. This is the other side of a coil. Suppose if this is the starting side of the coil, then this will be the ending side of the coil. Now, the electrical space angle between these two sides is what we will call it as coil pitch or coil span. Okay, very simple. Now, based on the value of this coil span or based on the value of coil pitch, coils are generally divided into two categories. Okay, one is full pitched coils, and other one is short pitch coils, also called as corded coils. I can simply write it as short pitched coils, also called as corded coils. Okay, as I told you, coils are divided into two categories based on the value of this coil span. First of all, what is meant by coil span? It is the electrical space angle between one side of a coil to other side of a coil. And based on the value of this coil span, coils are generally divided into two categories, full pitched coils and short pitched coils. Now, let us try to understand what is meant by full pitched coil and what is meant by short pitched coil. And also we will learn why short pitched coils are generally used for synchronous machines and induction machines. Okay. Alright. Now let us understand what is meant by full pitched coil. I wrote the definition very clearly. In this coil, coil span will be equal to one pole pitch. I told you already one pole pitch means it is always 180 degrees electrical. Suppose if a coil span is also equal to 180 degrees electrical, then it is called as a full pitched coil. Now see how this full pitched coil is going to be. Suppose let us assume a machine is having two poles. We have a north pole here and we have a south pole here. Now tell me what is the angle or distance from this north pole to south pole. This is called as one pole pitch. And one pole pitch is always equal to 180 degrees electrical. Now, a coil span is also equal to one pole pitch. That means, if one side of the coil is exactly under north pole, the other side of the coil is exactly under south pole. Practically, the machine will be circular in nature, but for mathematical analysis, I am taking a linear diagram. Okay. Suppose if this is how a coil existed, definitely this type of coil is called as a full pitched coil. Now see here, this is the starting of the coil and this is the ending of the coil. Now what is the distance between these two sides? Definitely that is equal to one pole pitch. That is nothing but coil span, and here the coil span beta is equal to 180 degrees. Okay. Beta is a letter we will use to indicate coil span. And don't forget that the letters may be different from different textbooks to other. In some of the textbooks they use it to write beta, some of the textbooks they use it to write alpha. Okay. But important thing is the definitions are important. Okay. Anyway, this is how a coil span is defined for a full pitched coil. Now, if the coil is a full pitched coil, then how to find out the resultant EMF of this coil? I wanted to know. Okay, let us say this is like a term A and this is like A dash. I wanted to calculate what is the voltage between this A and A dash. Let us imagine this is one side of the coil and it is under north pole. Okay, and I am taking north pole as reference. Reference means can I start with 0 degrees? Therefore, the other side which is exactly under south pole, this will be at how many degrees? 180 degrees. Therefore, if this coil side voltage is, let us say, E, it is at an angle 0 degrees, then this coil side voltage will be E at an angle 180 degrees. Am I right? Because both are exactly separated by 180 degrees in electrical. Okay. So, now find out what is the voltage between A to A dash. Can I write A to A dash means it is VA minus VA dash simply. It is the potential difference from A to A dash. What is VA? VA means first coil side voltage, that is E at an angle 0. Let me write here E at an angle 0 minus what is A dash voltage is E at an angle 180 degrees. Can I write minus at an angle 180 degrees is simply like plus at an angle 0 degrees. Therefore, what is the resultant voltage of a full pitched coil? Yes, that is equal to 2E. E plus E, that is equal to 2E. Then it looks like an algebraic summation or vectorial summation. It just looks like an algebraic summation. Even though we added vectorially, but because of that 180 degrees phase angle difference, the potential difference between these two nodes is just equal to algebraic summation. Even in case of a transformer also, the resultant voltage is always algebraic summation only. Suppose if there are two turns, if first turn voltage is E, second turn voltage is E, then what is the resultant transformer winding voltage? 2E. Therefore, a full pitched coil voltage is just like a concentrated winding voltage. This is how to calculate full pitched coil EMF. Okay. Now, let us understand what is meant by short pitched coil, and also we will see what is the advantage of a short pitched coil. Okay. Alright, now let us understand what is meant by short pitch coil. Short pitch coil is also called as corded coil. First read the definition. In this coil, coil span is less than 1 pole pitch, very simple. In full pitched coil, coil span is exactly equal to 1 pole pitch, but in short pitched coil, coil span is less than 1 pole pitch. Less than 1 pole pitch means indirectly less than 180 degrees. Such kind of coils are called as short pitched coils. Now, short pitched coils have advantages as well as disadvantages. First, let us see mathematically, then we will discuss about advantages and disadvantages. See here. First, let us consider this is a north pole we have in a machine, and this is the adjacent south pole. And what is the angle or distance between this north pole to south pole? This is called as 1 pole pitch, and 1 pole pitch is always equal to 180 degrees electrical. Now, suppose in case of a full pitched coil, if one coil side is exactly under north pole, the other coil side will be exactly under south pole. Such kind of coils are called as full pitched coils. But now we are discussing about short pitched coil where coil span is not exactly 180 degrees, it is less than 180 degrees. That means you see, suppose if this is one side of a coil, it is exactly under north pole. Now the other side of the coil not exactly under south pole, it is now short pitched. Okay, you see this? Definitely the coil span beta is less than 180 degrees. Suppose this is 180 degrees. Let us say coil span is now, let us say 160 degrees only. That means it is shorted by how many degrees? 20 degrees. So this small angle, this small angle by which the coil is shorted is called as short pitch angle, represented by a letter alpha. This alpha is called as short pitch angle. Okay, so therefore coil is shorted by alpha degrees. If alpha is the short pitch angle, then what is the coil span? Beta will be equal to, can I write beta will be just 180 degrees minus alpha. Let me write more clearly. So now coil span beta is equal to 180 degrees minus alpha. Okay. So coil pitch is not equal to 180 degrees. It is shorted by a small angle, and that small angle is called as short pitch angle. Therefore, if you take this north pole as a reference is always 0 degrees. Then this south pole is exactly 180 degrees, but this is 180 minus alpha. Therefore, tell me now, if this is A and this is A dash, can you tell me this coil side is exactly at how many degrees? 0 degrees. This coil side is exactly at how many degrees? I can write E at an angle 180 minus alpha. Therefore, what is the resultant voltage between these two nodes? That is nothing but the potential difference from A to A dash. So I can write VA dash is equal to VA minus VA dash. VA means first coil side voltage, that is E at an angle 0 minus E at an angle 180 minus alpha. I can write minus at an angle 180 as simply plus at an angle 0. Therefore, if you look at these two terms, is it looking like one vector is at an angle 0 degrees, the other vector is at an angle minus alpha degrees? Therefore, what is the phase angle between these two vectors? Alpha degrees is the phase angle. If two vectors are separated by alpha degrees, this is E at an angle 0, this is E at an angle minus alpha, then the resultant voltage is definitely vectorial summation or algebraic summation, vectorial summation. Therefore, can you tell me what is the resultant voltage is going to be here? Therefore, I can write the resultant coil voltage will be equal to square root of, I hope you have idea about vectorial summations, E square plus the other vector E square plus 2 into first vector E, second vector E into cos alpha. What is the common thing you can take? E square you can take common. Therefore, out of the root it becomes E into square root of 1 plus 1, 2 plus 2 cos alpha. And you can take root 2 also common. Then it becomes root 2 into E square root of 1 plus cos alpha. And you can write 1 plus cos alpha as 2 cos square alpha by 2. Root over 2 cos square alpha by 2 means you will get root 2 cos alpha by 2. Already one root 2 is there. What is the final mathematical equation? It becomes 2E cos alpha by 2. This is going to be the resultant coil voltage if we use full pitched coil or short pitched coil. Short pitched coil. So therefore, for a short pitched coil, the resultant voltage is equal to 2E into cos alpha by 2. And we observed that short pitched coil voltage is now just algebraic sum of these two EMFs or vectorial summation, okay, vectorial summation, because there was alpha phase angle difference, understand? And we also know that mathematically vectorial summation is always less than algebraic summation. Suppose when I consider full pitch coil, this is at an angle 0, this is at an angle 180, therefore the potential difference is simply algebraic sum of the two. What is the resultant voltage of a full pitch coil? 2E, algebraic summation. But this is definitely less than 2E since it is vectorial summation. That means you tell me what is the disadvantage of a short pitch coil if I ask you. Definitely short pitch coil voltage is a vectorial summation. Therefore, resultant voltage is less compared to full pitch coil voltage. Suppose if this is 50 and this is 50, resultant voltage will be 100 or less than 100? Less than 100. In a full pitch coil, if this is 50 and this is 50, resultant voltage is equal to 100, but in short pitch coil, it is less than 100. So, final answer is short pitch coil voltage is always less than full pitch coil voltage. How much less means it depends upon this alpha value. What is this alpha? Alpha is nothing but short pitch angle in electrical degrees. Don't forget that everything we are substituting in mathematical equations must be electrical degrees. Okay. In case if mechanical degrees are given in the problem, you have to convert to electrical degrees and then substitute the answer. So, how much voltage it is less compared to full pitch coil means it depends upon short pitch angle alpha. Okay. Now this is a disadvantage because short pitch coil voltage is less compared to full pitch coil voltage. Now coming to the advantage, there are multiple advantages. Let me discuss the first advantage directly, you can understand. You see, overhang length. You remember back end connections or overhang connections. They are also be designed using a copper winding only. Suppose if it is a full pitch coil, you see overhang connection will be up to 180 degrees. But if it is a short pitch coil, definitely overhang connection should be up to 180 or less than 180, less than 180. That means a short pitch coil requires less copper winding for overhang connection or more copper winding for overhang connection, less copper winding. You understand? When you are using less copper winding, obviously the weight of copper and the cost of copper will be slightly reduced. Not much, but slightly reduced. Okay, but that is not a big advantage. I can say it is one of the advantage only. There are big advantages of using a short pitch winding that we need to discuss now. Okay, all right. Once we have idea about full pitch coil and short pitch coil, now we need to learn about an important factor known as pitch factor. This is another important terminology of armature winding. So first let me give you the definition. Pitch factor is the ratio between a short pitch coil voltage to full pitch coil voltage. Very simple. I am repeating, it is the ratio between short pitch coil voltage to full pitch coil voltage. So numerator is voltage, denominator is also voltage. That's why it is a unitless quantity. Okay. So let me write here. Pitch factor is the ratio between a short pitch coil voltage to full pitch coil voltage. That's all. We just calculated what is the formula for short pitch coil voltage. Yes, that is the vectorial summation. We got equation 2E into cos alpha by 2. And what is the voltage of a full pitch coil? It like, algebraic summation, full pitch coil voltage is equal to 2E. So ultimately 2E will cancel. So therefore pitch factor is equal to cos alpha by 2. Pitch factor is equal to cos alpha by 2. Now, how this pitch factor is an important parameter in armature winding of synchronous machine. You see, suppose if you cross multiply this relation, can I write short pitch coil voltage is equal to full pitch coil voltage multiplied by pitch factor? Yes or not? Therefore, whenever you wanted to calculate what is the value of a short pitch coil voltage, you try to calculate first what is the full pitch coil voltage and then multiplied with pitch factor, we can get what is the value of short pitch coil voltage. This is what mathematically we will do. Why? Because finding full pitch coil voltage is very simple, because full pitch coil voltage is nothing but algebraic summation. Therefore, I can do it just like a transformer case. And then multiply with pitch factor so that you will get corresponding short pitch coil voltage. So this is what mathematically we will proceed. Always try to calculate algebraic sum value and then multiply by corresponding factor, we will get distributed coil voltage. So first find out full pitch coil voltage, multiply with pitch factor so that we will get a short pitch coil voltage. Understand? Fine. And always don't forget, a short pitch coil voltage is always less than a full pitch coil voltage. Okay, because short pitch coil voltage is vectorial sum, full pitch coil voltage is algebraic sum. And also you see pitch factor formula cos alpha by 2. We know that any angle except 0 degrees, cos of any angle except 0 degrees is always less than 1. That's why pitch factor is always less than 1. Suppose if it is a full pitch coil, what is alpha is equal to? Full pitch coil means, can I say coil span is equal to exactly 180 degrees. Therefore, it is shorted by any angle or not shorted. It is not at all shorted. That's why short pitch angle is equal to 0. If a short pitch angle is equal to 0, what is a cos 0 is equal to 1. Therefore, I can write for full pitch coil, pitch factor is equal to 1. And for short pitch coil, pitch factor is always less than 1. Because for short pitch coil, alpha is a finite value. any angle except 0 degrees is always less than 1. Cos of any angle except 0 degrees is always less than 1. Okay. So always try to calculate full pitch coil voltage first, multiply with pitch factor to get corresponding short pitch coil voltage. Now let us try to understand what is the benefit of using short pitch coils even though they are offering less voltage. Okay, let us see. Now coming to the point, we wanted to understand what is the advantage of using a short pitch coil over full pitch coil. We know that magnetic flux in any synchronous machine cannot be purely sinusoidal. Even though we are taking a lot of precautions and we are making so much effort to make it like a purely sinusoidal flux wave, it is never possible practically. Okay, in most of the alternators, especially cylindrical rotor synchronous generators, magnetic flux wave is like a flat topped waveform. Therefore, it consists of number of odd harmonics in it. Even though it is non-sinusoidal, it is symmetrical in nature. Therefore, even harmonic flux components will cancel, only odd harmonic flux components will be existed. Now, when harmonic components are existed in flux wave, definitely EMF wave also consists of harmonic components. When EMF wave has harmonic voltages, resultant voltage out of alternator will be non-sinusoidal in nature. If voltage is non-sinusoidal in nature, there are so many disadvantages in power system. Okay. So our ultimate aim is we wanted to supply a sinusoidal voltage to infinite busbar. To make voltage sinusoidal, you have to make sure that harmonic voltages do not appear. But practically, harmonic voltages will always be created. Why? Because flux is not sinusoidal purely. That's why I took a simple diagram here. I am drawing a diagram of a flux density waveform with respect to space angle theta, because magnetic field is spatially distributed. Okay. You see, this is the fundamental flux wave. Okay, this black color one is a fundamental flux wave. Like that, so many harmonic flux components will also be available. For example, I took a fifth harmonic flux component wave. Like that, third harmonic will be there, seventh harmonic will be there, ninth harmonic, 11th harmonic, all odd harmonic flux components will be existed. Now, this black color one is going to be the fundamental flux waveform. Let us say B1, fundamental flux density waveform. And you see, from here to here, how many fundamental cycles are completed? If you see the fundamental wave, can I say exactly one cycle is completed? One cycle means how many degrees? 360 degrees electrically. If a fundamental component completes one cycle, fifth harmonic will complete how many cycles? You see, 1, 2, 3, 4, 5. Am I right? Seventh harmonic will complete 7 cycles. Ninth harmonic 9 cycles. Therefore, this is fifth harmonic flux density waveform. Understand? Because it completes 5 cycles. Therefore, if a fundamental component, the total angle is equal to 360 degrees for one complete cycle, then fifth harmonic component completes 5 cycle. Therefore, what is the angle? 5 into 360 degrees. Because electrically, I told you, always remember electrical angle is important. Mathematically, electrically, one complete cycle is always equal to 360 degrees. Half cycle is 180 degrees. So for fundamental component, this distance is equal to 360 degrees. But for fifth harmonic, you see, one cycle means up to here itself it is 360. Another 360, 360, 360, like that 5 360s are there. Therefore, if a fundamental angle is 360, fifth harmonic flux component angle is 5 into 360. Similarly, if a fundamental angle is equal to theta, fifth harmonic component corresponding angle will be equal to 5 theta. If a fundamental short pitch angle is equal to alpha, fifth harmonic component short pitch angle is equal to 5 into alpha. That's all. Okay. Now let us understand. I will first consider a full pitch coil here, and then I will consider a short pitch coil. This is simple mathematics, nothing difficult. I told you, if you understand simple analogies with respect to phasor diagram, everything will be simple in a synchronous machine. I wanted to consider full pitch coil first. I will show you the disadvantage. Then I will consider a short pitch coil and I will show you the advantage. Okay. First of all, what is mean by a full pitch coil, you tell me? Full pitch coil means the coil span is exactly equal to one pole pitch, that is 180 degrees. Therefore, you see now, this is my reference. The maximum value of a fundamental component is the reference. Let us say one coil side is placed exactly here. Okay. Then after 180 degrees means, can I say negative maximum? If positive maximum is the 0 degrees, negative maximum is equal to 180 degrees. So here I have the other coil side. First let us talk about only fundamental, then we will talk about fifth harmonic. Can you tell me at this particular point fundamental component is positive maximum or negative maximum? Positive maximum. Therefore, it will induce a positive voltage across this coil. Let us say this is the positive voltage representation. Okay, fine. Next, at this point fundamental component is negative maximum. Therefore, it will induce negative voltage across the coil. You see the voltage polarity representation. This is plus minus positive voltage, minus plus negative voltage. Now these two are connected to each other. Therefore, you tell me what is the resultant fundamental voltage. Let us say E1. 1 indicates first harmonic fundamental. Can you tell me what is the resultant voltage is equal to 2E1. Okay, that means both voltages are adding. Fundamental voltages are added, very clear. Next, let us talk about fifth harmonic voltage now. Can you tell me at this particular point fifth harmonic is positive maximum or negative maximum? You see, fifth harmonic is negative maximum. At this particular point, can you tell me fifth harmonic is positive maximum or negative maximum? Positive maximum. Therefore, this is a fifth harmonic voltage. Now you tell me what is the resultant fifth harmonic voltage here? You see, this is negative. Negative is connected to positive. When negative is connected to positive, voltages are aiding or subtracting. When two opposite polarities are connected, definitely voltages are aiding. Therefore, resultant voltage is 2E5. That means you tell me, when I consider a full pitch coil, I hope you are listening very carefully. When I consider a full pitch coil, fundamental voltages are aiding. At the same time, fifth harmonic voltages are also aiding. When fundamental voltage, fifth harmonic voltage both are present, resultant voltage is definitely non-sinusoidal in nature. This is the disadvantage of a full pitch coil. Now, to overcome this disadvantage, I wanted to use a short pitch coil. Using a short pitch coil, my aim is fifth harmonic voltage must be equal to 0. If fifth harmonic voltage is equal to 0, then what is the only voltage available? Fundamental voltage only. Only fundamental voltage is available means resultant voltage becomes sinusoidal in nature. So what is our aim? Our aim is make resultant fifth harmonic voltage is equal to 0. Can I say resultant fifth harmonic voltage will be 0 if minus term is connected to again minus term? If minus is connected to minus, voltages will aid or subtract, resultant voltage becomes 0. So for that purpose, what I wanted to use is, I don't want to use full pitch coil anymore. I wanted to use a short pitch coil. So see, what I am doing is very simple. This is a full pitch coil voltage. Okay, this is 180 degrees because positive maximum to negative maximum, 180 degrees exactly. But I don't want to use a full pitch. I wanted to use a short pitch now. I wanted to use a short pitch in such a way that which harmonic voltage should cancel? Fifth harmonic. Now see here, exactly at this point, fifth harmonic is negative maximum or positive maximum? Negative maximum. This is fifth harmonic voltage, negative voltage. Now at this point, fifth harmonic voltage becomes positive. If this is negative, this is positive, both are aiding. But my aim is both must subtract. When these two voltages will subtract, suppose if I have negative here. To have negative, I have to use a short pitch winding now. What I will do is very simple. Remove the other coil side here and place the other coil side exactly here. You see. Now just imagine if I use a coil like this. Now you tell me up to here this is 180 degrees, but this is now, can I say less than 180 degrees? Definitely yes, definitely less than 180 degrees. Now let us talk about only fifth harmonic voltage. Here at this point fifth harmonic voltage is negative maximum, so the voltage is negative. Again at this point will you tell me what is the fifth harmonic sign? Negative maximum, therefore here also negative voltage will induce. You see now a minus polarity is connected again to minus polarity, therefore resultant voltage will subtract, and that means fifth harmonic resultant voltage becomes 0. If fifth harmonic voltage becomes 0, the resultant voltage will have only fundamental component. Only fundamental component means sinusoidal in nature. So this is the advantage of using short pitch coil. And will you tell me how much would be this short pitch angle? How much would be this short pitch angle? I should say alpha 5. Why I wrote alpha 5? Because I wanted to eliminate fifth harmonic voltage. Therefore, it is the short pitch angle used to eliminate for fifth harmonic. Can I say this alpha 5 is nothing but the angle from positive maximum of fifth harmonic voltage to negative maximum of fifth harmonic voltage? And if you calculate this angle, definitely that will be equal to 180 degrees by 5. Why? Because we know fundamentally this is how many degrees? Only negative half cycle. Only negative half cycle means 180 degrees. Okay? And out of this, for this entire 180 degrees, how many fifth harmonic cycles are there? 5 cycles are there. Therefore, from positive maximum to negative maximum, overall 180 degrees by 5. Therefore, the short pitch angle will be equal to 180 degrees by 5. There is no magic here. This is a simple geometry. Total angle is 180 degrees. Therefore, this angle will be exactly 180 degrees by 5. So, how much short pitch angle we have to use to eliminate fifth harmonic voltage? 180 degrees by 5. Similarly, if I ask you how much short pitch angle is required to eliminate seventh harmonic voltage? 180 degrees by 7. To eliminate ninth harmonic voltage, 180 degrees by 9. To eliminate 11th harmonic voltage, 180 degrees by 11. So like that, by using short pitch angle perfectly, we can eliminate harmonic EMFs from the output voltage of alternator. So geometrically we derived why short pitch angle should be 180 degrees by 5 exactly. Now let me do it mathematically. If I do it mathematically, it will be more clear for you. Okay. Okay, so now let us understand the pitch factor component for harmonic EMFs, okay, mathematically. As I told you, if a fundamental component completes one half cycle, fifth harmonic component in the same space can complete 5 half cycles. Seventh harmonic can complete 7 half cycles. Therefore, if a fundamental component space angle is theta, then fifth harmonic component space angle will be 5 theta, seventh harmonic component space angle will be 7 theta. Similarly, let us write pitch factor for various harmonic EMFs. So let me start with fundamental EMF pitch factor. Fundamental harmonic pitch factor. KP1. Okay, 1 indicates first harmonic, that is a fundamental harmonic. So the formula is cos alpha by 2, where alpha is fundamental short pitch angle fundamentally. Okay, right. Fine, electrical angle, don't forget that. Now let us write third harmonic pitch factor. Third harmonic pitch factor, let me write it as KP3. If fundamental space angle is alpha, then third harmonic space angle will be simply cos 3 alpha by 2. That's all. Similarly, what is the pitch factor for fifth harmonic EMF component? Yes, fifth harmonic KP5 cos 5 alpha by 2. Similarly, for seventh harmonic component, KP7 is equal to cos 7 alpha by 2. Therefore, the order will continue. Now, why it is important to learn about the pitch factor of various harmonics? Very simple. I told you, short pitch coil voltage is always equal to full pitch coil voltage multiplied by pitch factor. Yes or not? Suppose if pitch factor is equal to 0, what will be the short pitch coil voltage will be also equal to 0. That means if fifth harmonic pitch factor is, let us say, equal to 0, then fifth harmonic short pitch coil voltage also becomes 0. Suppose if seventh harmonic pitch factor is equal to 0, in that case seventh harmonic short pitch coil voltage is also 0. If harmonic EMF is 0, resultant voltage becomes purely sinusoidal. So, when you wanted to eliminate any harmonic voltage, the corresponding pitch factor should be made to 0. If pitch factor is equal to 0, automatically that corresponding EMF also made to 0. Let us talk about fifth harmonic voltage. First of all, I wanted to make fifth harmonic voltage to 0. That means fifth harmonic pitch factor should be equal to 0. Let me continue. So, I can write to eliminate fifth harmonic EMF. To eliminate fifth harmonic EMF. So, to eliminate fifth harmonic EMF, fifth harmonic pitch factor must be 0. Then automatically the corresponding EMF also 0. What is the pitch factor for fifth harmonic? Cos 5 alpha by 2 should be equal to 0. And we know cos of how much angle is always equal to 0? 90 degrees. That means 5 alpha by 2 should be equal to 90 degrees electrical. Always electrical angle we need to use. That means what is the short pitch angle required? 180 degrees by 5. Is it the same that I proved, graphically also by drawing a waveform? So therefore, the short pitch angle required to eliminate fifth harmonic EMF is equal to 180 degrees by 5. On the same manner, to eliminate seventh harmonic EMF, what is the short pitch angle required? On the same manner, alpha 7, it should be equal to 180 degrees by 7 electrical degrees. If I use this much short pitch angle, seventh harmonic EMF can be made to 0. If this is a short pitch angle used, fifth harmonic EMF can be made to 0. Okay. Now see here, I am always trying to say fifth harmonic to 0, seventh harmonic to 0, but I am not talking about third harmonic to 0. Why? Because third harmonic is one of the major harmonic. After fundamental, the most effective harmonic is third harmonic component. But I am not talking about any condition to make third harmonic EMF to 0, because I told you inherently in most of the synchronous generators, armature winding will be designed to have a star connection. And you studied in transformers course also. Suppose if the winding is star connected, even though phase voltages are having a third harmonic EMF, when you come to line voltages, third harmonic EMF becomes 0. I hope you remember that. Phase voltages may have third harmonic EMF because third harmonic EMF is 0 sequence. And when you calculate line voltages, the third harmonic voltages will cancel, then third harmonic voltage in a line voltage components is equal to 0. That's why in a star connected winding, third harmonic EMF is not effective. If it is a delta connected winding, then third harmonic EMF is effective. But as I told you, in majority of synchronous machines cases, armature winding is star connected. That's why the line voltages do not have a third harmonic EMF component. If third harmonic EMF components are not available, then what are the effective voltages? Fundamental, next fifth, seventh. Again, ninth harmonic EMF also will not be available in line voltages because ninth harmonic is also 0 sequence. And then the next effective is 11th harmonic. But we know one thing, as the harmonic number is increasing, the magnitude of that harmonic voltage will decrease. Therefore, higher order voltages can be neglected. If higher order harmonic voltages are neglected, what are the effective harmonic voltages always? Fifth order harmonic and seventh. fifth order harmonic and seventh order harmonic voltages. Third harmonic is also effective, but line voltages, third harmonic voltage will not be available. Therefore, no need to eliminate third harmonic specifically. It is automatically getting cancelled. So our effort is always trying to make fifth harmonic voltage and seventh harmonic voltage is equal to 0. Suppose if I use a short pitch angle 180 degrees by 5, fifth harmonic voltage becomes 0, but seventh harmonic will be available. If I use a short pitch angle 180 degrees by 7, seventh harmonic voltage becomes 0, but fifth harmonic voltage will be available. But my aim is I wanted to make both harmonic voltages to 0. In that case, neither you use 180 by 5 nor 180 by 7, take the average between the two and use that value to eliminate both fifth harmonic as well as seventh harmonic EMF to 0. So let me write clearly here. So to eliminate the effect of both fifth and seventh harmonic EMFs, we have to use a short pitch angle which is the average between these two. Okay. So therefore, the alpha should be average between alpha 5 and alpha 7. Alpha 5 is 180 degrees by 5. Alpha 7 is 180 degrees by 7. And take the average between the two and it will become approximately 30 degrees electrical, approximately. If you use this much short pitch angle, fifth harmonic will be almost made to 0. You can't make to exactly 0 because if you wanted to make fifth harmonic exactly 0, you must use 180 by 5 which is exactly 36 degrees. But am I using exactly 36 or almost 36? Almost 36. Therefore, when I use this average concept, I cannot make fifth harmonic voltage completely to 0, but I can eliminate it by 90%. Similarly, seventh harmonic voltage can also be eliminated by 90%. So, I can say the remaining small component can be neglected. Okay. So, therefore, use the average between these two so that fifth and seventh harmonic voltages are almost nullified. When fifth and seventh harmonic voltages are almost nullified, higher order harmonics are neglected, then what is the only voltage that will be effective out of the machine? Fundamental EMF. Only fundamental EMF means resultant voltage becomes purely sinusoidal. Never take a separate action to eliminate third harmonic EMF to 0 because line voltages, third harmonic voltage will always cancel. Only problem with fifth and seventh. Therefore, take the average angle between the two. Therefore, we can eliminate the effect of fifth and seventh harmonic voltages also, so that final resultant voltage becomes purely sinusoidal. So this is the advantage of using short pitch coils over full pitch coils. So finally, what are the summary points? Full pitch coil can generate more voltage because algebraic sum. Short pitch coil voltage is less because vectorial sum. But full pitch coil will have harmonic voltages also. We can't eliminate harmonic voltages. But in short pitch coil, harmonic voltages can be eliminated. Therefore, resultant voltage becomes more sinusoidal. Okay. Now let me write a generalized equation to understand the short pitch angle required. Yes, the question is short pitch angle to eliminate nth harmonic EMF. Okay. To eliminate fifth harmonic EMF, what is the short pitch angle required? 180 degrees by 5. To eliminate seventh harmonic EMF, 180 degrees by 7. To eliminate nth harmonic EMF, what is the short pitch angle required? 180 degrees by n. For fifth harmonic 180 by 5, seventh harmonic 180 by 7. For nth harmonic, the short pitch angle required is 180 degrees by n. If this is a short pitch angle required to eliminate nth harmonic EMF, then what is the coil span during this condition? We know coil span beta is always equal to 180 degrees my short pitch angle alpha, because this is the coil. This is coil span beta. This is the full pitch 180 degrees. This is short pitch angle alpha. Then what is beta is equal to 180 minus alpha. And what is the alpha value right now to eliminate nth harmonic? 180 degrees by n electrical degrees. And if you take 180 common, it will become 1 minus 1 by n times of 180 degrees electrical. Can I write 180 degrees electrical is nothing but full pitch? Yes or not? Or pole pitch? Therefore, it is 1 minus 1 by n times of full pitch. So, this is the coil pitch or coil span required to eliminate which harmonic EMF? Nth harmonic EMF. You replace n is equal to 5 here, coil span to eliminate 5th harmonic EMF. N7 here, coil span to eliminate 7th harmonic EMF. N11 here, coil span to eliminate 11th harmonic EMF. Don't substitute 3 here because 3rd harmonic EMF we won't eliminate separately, it will be automatically cancelled in line terminals. Okay. So this is about short pitch coils. Okay. Now I will conclude the lecture here. We studied about short pitch coils. In the next lecture we will try to solve a few numerical questions related to short pitch coils, and then we will discuss the further terminology of EMF equation. Okay, so I am dividing EMF equation into 2 lectures. One lecture is completed, and the next lecture we will complete the remaining portion of EMF equation. Okay, thank you.